Hi, everyone. So the session today is going to be AMSI Unchained. We're going to review some known AMSI-bypass techniques and introduce new one as well. First of all, I want to say it's a great honor to be here, and thank you for attending my presentation. My name is Maor Korkos. I'm a security researcher, team leader at Deep Instinct for the last 2 years. I previously was a vulnerability researcher, and fun fact, I'm supposed to get married in 10 days if my fiance won't kill me for being here. Agenda for today. We're going to start with an AMSI overview and AMSI architecture. We'll move on to examine some AMSI-bypass techniques, known AMSI-bypass techniques, and see what security vendors are trying to do in order to prevent and detect those techniques. Then we'll move on to present new AMSI-bypass techniques, and in order to do so, we'll have to deep dive into the AMSI internals. Anti-malware scan interface, or as some call AMSI, or as I sometimes call AMSI-dumpty, is an interface standard that allows applications to integrate with anti-malware products. In scriptable applications, for example, at the point when a script is ready to be supplied to the scripting engine, the application can call the Windows APIs to request a scan of the content prior to its execution. The architecture of AMSI is designed so any consumer, any application which is a consumer can request content to be scanned, and any security vendor, which is a provider, can register to receive scan requests. The OS is the mediator. It is implemented as a DLL named AMSI.dll that must be loaded into any AMSI-protected application. AMSI has seen increased adoption in recent years as it was integrated into many applications and OS components and leveraged by endpoint solutions to gain additional access and visibility to critical and widely exploited attack surfaces, notably script engines, Office macros, WMI, .NET, and UAC. We can see on the left side, example for consumers, PowerShell from version 3. It's inbuilt consumers that consumes AMSI services for today. JavaScript, VBA, WMI, UAC elevations, and the new ones are Excel 4 macros, volume shadow copies operations, and .NET in-memory assembly loads. All of these consumers consumes AMSI services. On the right side, we can see security vendors that implement AMSI providers, such as Microsoft Defender, Deep Instinct, SentinelOne, and so on. Beside from the built-in consumers, any developer can choose to consume the AMSI services. What he needs to do is basically to load the AMSI DLL into his memory space and call several exports, several functions that this DLL declares. We're going to talk today about AMSI Initialize, AMSI Open Session, AMSI Scan Buffer, and some more exports. AMSI Initialize is a function that initializes AMSI for us. AMSI Open Session opens a new AMSI session. And AMSI Scan Buffer full of content for malicious indicators. AMSI Scan Buffer will return an AMSI result. The values of the AMSI result can vary, but the most important one of them are the AMSI result clean, AMSI result undetected, and AMSI result detected, which indicates that the malicious indicator was found. The process memory layout of an AMSI-protected application will look like this, will always look like this. AMSI-DL is going to be loaded into the memory space, and a struct named age AMSI context need to be initialized. Every time we want to initialize the AMSI services, we need to call the AMSI initialize export. It receives two parameters, the application name that's going to consume the AMSI services, and the reference to the age AMSI context structure. This structure is going to hold 4 attributes: signature, application name, anti-malware, and session count. After AMSI initialize was called, it's going to fill these attributes with the appropriate values. The signature will always be AMSI, which identifies this struct in memory. The application name is going to be the application name that was received as a parameter. Anti-malware is going to be an instance of a class named CAMSI anti-malware. We're going to see deeper lately how it works. And the session count is going to be a random number. Each time we want to make a scan request, the developer needs to call a function named AMSI Scan Buffer. It receives the AMSI context, the content that we want to scan, and the reference to an AMSI result. as we already seen. At each time we're going to make a scan request, AMSI scan buffer is going to call a function named scan that declared by the C AMSI until malware class. And this function is going to loop to all the providers that are installed in the machine and call another function they exports, which also named scan. Again, we're going to see how this process works much deeper lately in the presentation. So now we covered how AMSI architecture looks like, and we'll move on to examine some AMSI-bypass techniques and see what security vendors are trying to do to prevent and detect from those techniques. But first, let's talk about the attack surface. Let's say we're an attacker that wants our bad content to be executed without being blocked. In the most basic form of AMSI provider, the anti-malware vendor can make a list of unallowed strings, which are malicious strings, and detect if the content that is going to be scanned contains one of these substrings, one of these malicious substrings. In this case, the attacker can basically try to manipulate, obfuscate, or encode these strings in order to bypass the provider's checks. We can take a look on the right side. This is the provider implementation of Microsoft Defender. And as we can see, when we try to run invoke Mimikatz, it's going to be blocked because it contains the Mimikatz substring. But if we split the string into invoke Mimikatz, the command is going to be executed, but it will pass the provider's checks. This is basically not an AMSI bypass, but a provider scan bypass that won't surely bypass all the providers in the market. Furthermore, the AMSI standard was written in recognition of those limitations and is based on scanning each script block that is going to be executed. That means that if the script was generated at runtime and went through several phases of the obfuscation, like when invoke expression is being used, and each execution is going to be scanned. A much more powerful option for an attacker will be to disable AMSI and free himself from the provider's checks for the rest of the execution. What we need to do in order to disable AMSI? AMSI is built as a chain of 3 components: the consumers, the mediator, which is the AMSI.dll, and the providers. If you want to disable AMSI, all we need to do is to break one of the links in this chain. Breaking is possible because the attacker runs in the same memory space with all of the AMSI components. The first link in the chain is the consumer. Each consumer implements code that consumes the AMSI services. If an attacker can reverse this code and understand how the consumer works, he might be able to interfere with the scan requests that are going to be made by the consumer. The example we are going to talk about today and that will accompany us for the rest of the presentation, it's PowerShell. And it's one of the most obvious examples. PowerShell implements its AMSI consumer and code components as a class named AMSI utils. Each time a script block is compiled, and just before it's going to be executed, PowerShell calls a function named perform security checks. We can see it on the right side. This is the used by feature in DNSpy. This function passes the script block content to another function named scan content that is responsible for the AMSI checks. Now we can take a look at the scan content function. We see that in the start of this function is going to refer a variable named AMSI init failed. If this variable is true, we're going to return AMSI result not detected without even going to scan the buffer. Afterwards, we will refer, the function is going to refer another variable named AMSI context. If it's null, it's going to try to initialize AMSI again. And if the initialization process fails, it's going to set AMSI init failed again to true and return AMSI result not detected. AMSI init failed variable really means that the AMSI initialization process has failed. So this is the purpose of this variable. It does the same for AMSI session and AMSI open session, and after all this preparation, it's going to finally scan the buffer by calling AMSI scan buffer that we've seen earlier. If the process fails, it's going to return AMSI result not detected, and if it doesn't fail, then it's going to return the appropriate AMSI result. One of the first introduced AMSI bypass techniques was published by Mike Graeber. With a one-line AMSI bypass script, he was able to take advantage of the power of reflection and perform direct access to the AMSI init failed variable, and basically set it to true. If we take a look 2 slides before, we can see that when AMSI init failed is true, then the scan request is not going to be made, and it's just going to return AMSI result not detected, no matter what content was going to be scanned. Another variant of this attack is to set AMSI session variable to null and corrupt the AMSI context, which means we will hit the first if statement in the slide. We'll see that AMSI session is null, and we'll try to call AMSI open session, but it will fail because AMSI context is going to be corrupted. And again, AMSI init fail is going to be set to true, and we return AMSI result not detected, which means the script is going to be executed no matter what content was in it. So what can security vendors do? The first option is to hook .NET set value function and prevent any direct access to AMSI init failed, AMSI session, or AMSI context. Another option is to hook the pre and post 3-blocked execution functions. There is a possibility to do so, and detect any change in the AMSI init failed variable from false to true that wasn't caused by AMSI uninitialize, which means that something fishy has happened. Now let's move to the next link in the chain, AMSI.dll. This is a major component of AMSI. It's an OS implemented DLL. And its function as the connector between the managed AMSI application and the COM anti-malware providers. The first option to break this link in the chain can be done by code patching. AMSI scan buffer, as we've seen, is the function that is implemented by the AMSI.dll as an export of AMSI.dll, and is responsible for scanning a buffer. What we can do is patch any part of this function or any other code components that are being called by this function in order to make it fail without filling the appropriate AMSI result. So another bypass script that was published by Rastamaus and is also implemented in PowerShell, as you see, this is the most popular implementation of AMSI-bypass techniques, but it doesn't really have to be PowerShell. It can be any other AMSI-protected application. Is to basically call add type functionality in order to be able to call Windows APIs. We don't necessarily have to call add type, but there's other options to call Windows APIs, but we won't cover them today. So in the first line, we're going to get an handle to the AMSI.dll, then find the POC address of AMSI scan buffer. Then we change the protection of the page where AMSI scan buffer resides in. And then we'll reach the final stage when we'll copy the patch and patch the prolog bytes of AMSI scan buffer, so they will return in valid argument. This is basically the opcodes that are written in the slide. In this case, AMSI scan buffer is going to fail and return without filling the appropriate AMSI result, and as so, the script is going to be allowed to execute. Another option to break this link in the chain is to use the data patching option. If we'll take a look at the AMSI scan buffer, we can see that at the start of the function, it validates the content of the AMSI context. AMSI context is passed to AMSI scan buffer as a parameter. And if we will be able to corrupt the AMSI context, we will be able to interfere with any scan request because, as we see on the right side, it's not going to perform the scan request if this structure is corrupted. What we can do in order to find this structure in memory, it's not so reliable, but we can try to find the AMSI signature or find in a global pointer that will point to this signature. But again, this is not such a reliable or easy techniques to do. So what security vendors are currently doing? Microsoft Defender AMSI provider choose to handle these AMSI bypass techniques by declaring that each string that are connected to these bypass techniques is malicious, like AMSI scan buffer, as well as AMSI scan string, RTL move memory, copy memory, AMSI utils, and so on. An attacker can bypass these restrictions by finding function addresses by names of neighbor functions, scan memory for code patterns, or even dynamically parse the LDR. A better approach of security vendors will be to monitor any permission change of any page inside the code section of AMSI.dll. And in order to handle the data patching, we can try to hook AMSI scan buffer and basically scan between any scan request that make sure that the AMSI context wasn't changed. That is equal to the AMSI context that was initialized in AMSI initialize. The last link in the chain is the AMSI providers. This is the code that's responsible to scan the content that was supplied to it by the consumer and decide if it's malicious or not. In order to be able to register a provider, any AMSI provider needs to create a CLSID entry in the HKLM software classes CLSID registry key, and registering the same CLSID in HKLM software Microsoft AMSI providers. When AMSI is initialized in the host process, it will enumerate each CLSID listed in the provider's registry key and initialize the COM object by importing the DLL in the in-proc server subkey in the HKLM software classes CLSID. If you want to sum it up, you can take a look at the picture on the bottom. You can see that the in-proc server subkey, this is basically the CLSID of Microsoft Defender, implementation of AMSI provider. We can see that it declares a subkey named in-proc server 32. And this subkey lists the path of the DLL. This is basically the AMSI provider itself. It contains all the code and all the things that are relevant to this provider. Each AMSI provider that wants to supply anti-malware services needs to implement an interface named anti-malware provider. This interface declares three functions: scan, close session, and display name. And this is basically the main principle of AMSI, the ability to scan content. If you want to break the last link in the chain, the only known techniques that exist right now is to use COM server hijacking, which means to go to this specific registry key and modify the path of the DLL so it will point to a corrupted DLL that won't function as the same AMSI provider DLL. There are some more AMSI-bypass techniques. Since AMSI launching, AMSI-bypass techniques have popped up like mushrooms after a rain. Researchers have noticed that PowerShell version 2 is still available to use in modern Windows machines, although it predates AMSI. There is also possibility to use any other old version of an AMSI-protected application that doesn't use AMSI. There is also an option to use DLL hijack of the AMSI DLL, copy an instance of the AMSI protected application to another folder, which contains a corrupted AMSI DLL, and then this application is going to load the AMSI DLL, this corrupted AMSI DLL instead of the original one. We can also try to compile our own version of the AMSI protected application and without the AMSI calls. Another option that is not listed in here is implemented by SharpBlock, and it is to put an outboard breakpoint on the AMSI scan buffer function, and when the breakpoint will hit, to revoke the code outside of AMSI scan buffer. All of these techniques are known and can be detected by some security vendors. So we've reached the second part of the presentation when we're going to show the new bypass techniques. In order to show them, we'll have to also deep dive into AMSI internals. The new techniques are basically going to patch an unmonitored memory outside the AMSI DLL area, the providers themselves. But before we're going to show them, let's go back to AMSI initialize. Any function that wants to use AMSI services must first call AMSI initialize. Before we continue, I want to mention that AMSI DLL is undocumented, so all the code we are going to see right now was reverse engineered and are simplified for reasons of convenience and understanding. And bear with me, it's going to be a little tough. This is how AMSI initialize look like. First of all, it's going to refer the first attribute in the AMSI context and set it to AMSI string, the signature attribute. Then it will refer the app name attribute and set it to the application name that it received as a parameter. It will also set the session count to a random number, and in order to fill the anti-malware attribute, we're going to create a new instance of an interface named iAnti-malware. When we're going to create a new instance of this interface, we're going to result in creating a new instance of a class named CAMSI-anti-malware. This class implements the iAnti-malware interface, and so on. So it must also declare two functions: close session and scan. And like we said, the new instance of this class is going to be assigned to the anti-malware attribute of the AMSI context. During the construction of the AMSI anti-malware class, a function named final construct is going to be called. And this function is going to call another function named AMSI create providers. AMSI create providers is going to receive as a parameter, is going to receive multiple parameters. The first parameter and the most important one of them is another attribute of the AMSI anti-malware class. And this attribute is going to hold the list of all the providers that are installed in the machine. AMSI create providers looks like this. It's very intuitive. It's going to enum all the subkeys under the software Microsoft AMSI provider registry key, all the CLS IDs that are mentioned in this registry key. And the max number of them are 16. And for each CLS ID, it's going to call another function named AMSI secure loading proc server that receives two parameters, the CLS ID that we want to load, and a pointer that would represent the provider. This pointer that we're going to give as a parameter is going to be assigned later to the AMSI anti-malware providers list that are being held by the AMSI anti-malware class. AMSI secure loading proc server looks like this. If you listened in the last slides, you can really assume what it's going to do, really guess. It's going to enum the software classes CLS ID registry key and find in this registry key for each CLS ID the subkey named inproc server 32. We've seen that this subkey holds the path of the DLL of the AMSI provider. Then we're going to load this DLL and call an export that it defines named DLL get class object. DLL get class object obtains a pointer to the provider's .i class factory object. Then we're going to create a new instance of an object that implements the anti-malware provider interface. As we've seen, this interface is the main logic, it constitutes as the main principle of AMSI, and this is what the provider needs to implement: the scan function, display name, and the close session. So when we create a new instance of this interface, we're going to create a new object that represents what the provider provides, which are these functions that must be declared by the anti-malware provider interface. Then the new instance of this object is going to be returned to the function that called this function, that called AMSI secure loading proc server. And as we already seen, we're going to assign it to the anti-malware provider list inside the AMSI anti-malware object. So the first provider patch, like we said, going to patch not so intuitive place to protect, the provider itself. We're going to patch the prolog bytes of the DLL get class object function in the provider's DLLs and interfere with the initialization process of AMSI. But first, we need to handle a small issue. Okay, I think that there's a slide missing here. Doesn't matter. Before DLL get object is going to be called, when our bypass script is going to be executed, DLL get object is not supposed to be called because this function is being called only during the AMSI initialization process. So if we will patch this function without doing anything else, then we won't really eat the patch we already did. So in order to eat the patch, we'll have to find a way to uninitialize AMSI and make AMSI to try to initialize again. So what we can do is take a better look at the consumer. First of all, it doesn't mention here because the slide is missing. I don't know why. But when we try to, if we take a look at the exports of AMSI, we can see a function named AMSI uninitialize that received a parameter which his name is the AMSI context, which is the AMSI context. It disables, it uninitializes only the AMSI context that was initialized first of all with AMSI initialize. So if we want to call AMSI uninitialized, we'll have to supply it the original AMSI context. But in order to do so, we need to find the AMSI context in memory, and as we've seen, it's not an so intuitive thing to do because it's not so reliable. Another option we can take is to look better at the consumer. Each consumer has a code that uninitializes AMSI for us. In PowerShell, we can use reflection to call this code. So if we take a look at the AMSI utils class that are implemented by PowerShell, we will see a function named uninitialize. This function is going to take the AMSI context that was initialized first and call AMSI uninitialize with this specific context. So basically, it's going to uninitialize AMSI for us without us being needed to provide the AMSI context to the AMSI uninitialized export. After all the preparations, after all the slides, we can finally hit the final bypass script. This is the first bypass script. We're going to use add type in order to call Windows APIs, basically very much like the AMSI scan buffer technique that we've seen. Then we're going to load to get an handle to put the provider DLL, which is MP-OAV in case of Microsoft Defender. Find the pork address of the get class object. Patch it, change the protection of the page the DLL class object resides in, and copy a patch that will return in valid argument, very much like the AMSI scan buffer techniques that we already seen, but without touching the AMSI DLL memory space that's supposed to be protected. Then, in order to make the DLL get class object code to be invoked, we're going to uninitialize AMSI. In order to do so, we're going to use reflection, find the uninitialize function in memory, and invoke it. So in the next time that a scan request is going to be made, the PowerShell is going to try to reinitialize AMSI, but it's going to fail because the DLL get class object was patched. This example is patching only the provider's DLL of MP-OAV. A more sophisticated one will be to query all the registry keys that we already see and find the provider's DLL names and patching each one of them. Another option is to know what are all the possibilities for providers that are in the market, try to load each DLL, and if we fail, if we succeed, we can assume that this DLL in memory, and we can patch it, and we need to patch it in order to bypass AMSI. The second bypass script is going to be based on scanning interception instead of initialization interception. Scanning interception is the classic way to disable AMSI. And as we've seen, we can implement this by basically patching the AMSI scan buffer function. Another option we can do, but again, like we've seen, AMSI scan buffer function is really monitored, and it's a memory area that we don't want to touch right now. Another option we can do is better look at AMSI scan buffer and understand how this process works. And when we will understand how this process works, we'll be able to interfere scan requests. AMSI scan buffer looks like this. First, it's going to validate the AMSI context that was supplied to it as a parameter. Then it's going to create a new instance of a class named CAMSI buffer stream that will represent the buffer that we're going to scan. Then we're going to refer the anti-malware attribute inside the AMSI context and call a function named scan from this attribute. And provided the buffer stream and the AMSI result. As we've seen, anti-malware attribute holds the CAMSI anti-malware holds an instance of the CAMSI anti-malware class. So eventually, we're going to execute the CAMSI anti-malware class with the scan function of the CAMSI anti-malware class. And this function looks like this. It's pretty intuitive. We're going to go to the list of all the providers that are being held by the CAMSI anti-malware class and loop through all the providers in this list. For each provider, we're going to call the scan function that, as we've seen, each provider must implement because it implements the anti-malware provider interface. And pass it the buffer stream that we want to scan and a reference to an AMSI result. Then the flow is going to check the AMSI result that was returned by each provider. If it's a bad result, which means that it's greater than 8,000 in X, the loop is going to break, and we're going to return without even continue to scan with the other providers. If all the providers return a good result, which means AMSI result not detected or AMSI result clean, we're going to finally return the AMSI result clean function. We can also return other options of AMSI result, but this code, like I said, is stripped. For simplicity, we're not going to cover this today. So, in the first bypass script, finding the place in the provider that we wanted to patch was pretty easy because the function that it exported was, the function DLL get class object was exported. So we could call the getProc process API in order to receive the function address. In this case, the scan function of the provider that I'm going to tell you, this is the function that we want to patch, is not so intuitive to find because it's not exported by the DLL. So we'll have to do a little trick. We're going to call AMSI initialize, and basically this will allocate a new age AMSI context for us. This age AMSI context will hold in its third attribute the new instance of the C AMSI anti-malware class. If we corrupt anything inside this class, it will only affect scan requests that are going to be made by this specific AMSI context. So it's not so good. It won't disable AMSI because all the scan requests will probably be with another AMSI context. But if we'll take a better look at the AMSI context in memory, we can see that the third attribute is going to hold the new instance of the C AMSI anti-malware of the anti-malware provider list. And each record in this list is going to be basically a new object of the anti-malware provider interface. And this object will finally always, each time we call AMSI initialize, will always point to the same scan functions inside the provider DLL. So if we'll be able to initialize AMSI and receive a new context, we can parse the context in memory and be able to find the scan function of each provider without calling any other Windows API. The final script will look like this. We can call AMSI initialize with Windows API, or we might also be able to call AMSI initialize that was implemented by PowerShell. We don't really have to do this with Windows API. As we've seen, AMSI utils class implements also an init function that initializes AMSI and receives an AMSI context. Then we loop through all the list of the providers that are being held by the C AMSI anti-malware object. First of all, in order to do so, we're going to refer to the third attribute of the context, which is going to be in, if we're talking about, this script is implemented on 32-bit applications. It is relevant to all the versions of PowerShell, including the old ones, because the C AMSI anti-malware class didn't change between versions. And if you want to do this the same for 64-bit applications, it is possible. All you need to do is to do a little reverse engineering process. But as we said, this is for 32-bit applications. So we're going to refer the third attribute, which is the new instance of the C AMSI anti-malware class. Then we'll go to offset 36. This is the list of the providers in 32-bit application will always be in offset 36. We loop to each provider in this list, find its vtable. The vtable is going to point to all the functions that must be implemented by this class, and the force function will always be the scan function. Force function in 32-bit applications means in offset 12. Then when we found the scan function, we just need to change the protection of the page where this function resides in and copy the patch that we want to apply to this function. This is basically going to patch the prolog bytes of the scan function inside the provider and return 0. So this function is going to fail without filling the appropriate AMSI result. Okay, let's see a demo. Okay, yeah. First step. At the beginning, let's try to call invoke mimikatz. In this case, we suppose that we're going to be blocked by the AMSI provider's scans because it contains the substring mimikatz. Now, this is the same instance of PowerShell that I already ran the bypass script, so I already bypassed the script. Sorry about it. Okay, let's run bypass PowerShell again. And now we are being blocked by the provider of Defender, the AMSI provider of Defender. Let's run the bypass script. This is the same bypass script in the presentation. Now try to call invoke mimikatz, and we are able to do so. From now on, as we already seen in the first instance of PowerShell that I closed, we'll be able to execute any script that we want, invoke mimikatz, I don't know, powersploit, whatever you wish to run, without AMSI scans to intercept us during this process. Takeaways. Destruction operation is easier because the AMSI-DLL and the provider DLL are loaded to the same memory space where a potential attacker lives. AMSI was not designed to prevent such attacks, and the current prevention or detection techniques of AMSI-bypass doesn't bridge this gap. From a security vendor perspective, security vendors should consider to protect the provider's memory as well as the AMSI-DLL memory space. And from a research perspective, uninitialization of AMSI might let us find new methods for disabling AMSI by interfering with the initialization process. This is different from the current techniques that interfere with the scanning process. Further research can also be done on AMSI scan interception and AMSI initialization interception. In scan interception, we can patch other code or data sections inside the AMSI DLL or the provider's DLL. In initialization interception, we can patch other involved DLLs like Combase or any other DLLs that are related to the scan process, to the initialization process. We can also try to use the patching of AMSI DLL, but it's not so reliable and easy technique to do. And RPC interception is another option that depends on the implementation of the provider. If we're talking about Microsoft Defender, it performs RPC requests, and because we are living in the same memory space as the provider, we might be able to intercept RPC requests that are being made by the Defender provider. I want to add that all the POCs that I presented today is going to be uploaded to my Twitter account on the left corner. And thank you for listening. And if you have any question,